until the daddy takes the T-bird away. Okay, so tonight we talk about the development of the dimensionless variables. And again, for the math ladies, we're going to convert these stupid problems into something you can solve. You okay? You like to sit on your book? You like to sit on your laptop? It's just your way of making sure the petties don't steal it? All right, now I'm really confused. So tonight what we'll do is we'll convert the partial differential equation that we derived, known as the diffusivity equation, into a dimensionless form. If you don't like PD, TD, etc., Gabe, wave your hands. Okay, she's in. No problem. Think of it as Y, X, and T, or something like that. Okay, it'll look just like any other math problem when we're done. And again, the reason we're investing all this time and effort in setting up the problem is to make it easy to solve. Okay, so the first thing we'll do is set up the problem in dimensionless form, and then the second part of this lecture, so I think this is going to probably be about 30 minutes, maybe a little bit less. The next part will be the Boltzmann Transform. And while I've got my brain on it, does anybody know why we call these things transforms? What do they transform from and to? Does anyone? The Boltzmann transform is an unusual one. Most are some sort of an integral transform, but it should actually just be called the Boltzmann Substitution. You're going to substitute the definition of an alternate variable, and that alternate variable is going to convert that partial differential equation into an ordinary differential equation. So obviously that variable has to have what in it? Distance and time, okay, or dimensionless distance and dimensionless time, okay? So we'll talk about that in a minute. The problem with the Boltzmann transform, and I want you to keep this in mind, is that it's a trick, okay? Math ladies, we can't say trick, right? It's a unique situation where the Boltzmann transform, everything complies to make it work. What is everything? The inner boundary condition, the outer boundary condition, and the initial condition all have to be such that whenever you take three variables and reduce to two, they're still compliant, okay? And that's going to only be one case for our purposes. So it is a very convenient trick. You'll like it, but it's not going to be something that's going to apply to something else. Okay, so now back to dimensionless variables. Again, what do we have? We have pressure, we have time, and we have distance. Logically, time and distance, no problem. There's a characteristic time, we don't know what it is. There's a characteristic distance. What would your choice for characteristic distance be, Alex? Okay, obviously you've read ahead. That is it. Okay, but Muscat, remember last night we talked about him, everything was in terms of density. Well, his reference distance was the external radius of the reservoir, not the wellbore radius. So there's a little bit of a difference there. When you go back and read his papers, you have to remind yourself. And again, you can choose whatever you want, but it has to be consistent. And fortunately for distance, it's pretty obvious. Okay, what is the distance going to be for fractured wells? Exactly. I'm glad you said fracture half length, not fracture length, because there's two. We assume two equal length fractures. Now we switch when we do what? When we go to the horizontal well, what is the horizontal well characteristic distance? It's the entire horizontal well length. At any rate, that you guys got it now. Okay, but for this case, it'll be the wellbore radius. Now, what's the characteristic pressure? Oops. We can't really define in terms of pressure because pressure has a specific scalar value, and the initial pressure is different for every case. But what's the same for every case? What's the pressure drop at time equals 0? 0. So we will use pressure drop instead of pressure, and that way we will always have a condition where the pressure drop, or the dimensionless pressure drop, at time equals 0 or dimensionless time equals 0 is 0. And I'm not going to get into your trap math, ladies. We're not going to argue about infinity. You've really got me thinking about that. But we will have an outer boundary condition that is infinity. And we will have an inner boundary condition that's 1, and we'll have an outer boundary condition that's 0. So we'll have several different cases here. Okay? All right, so as I mentioned, we're going to start by converting the dimensional radial flow diffusivity equation into dimensionless forms. We're going to initially assume that there's a common uniform initial pressure in the reservoir. So that means that the pressure at all points in the reservoir at time 0 or less than 0 is equal to the initial pressure. The inner boundary condition is given by a constant wellbore rate. You'll notice that this term on the left-hand side looks like Darcy's law. It's recast in dimensionless form, and that's exactly what it is. So we're going to determine this value of 1 from Darcy's law, okay? And then we have the infinite acting outer boundary condition, where when we have no reservoir boundary, if we continue to walk towards infinity, the pressure becomes the initial pressure, or the dimensionless pressure becomes 0. The no-flow outer boundary says that the gradient at the outer boundary is equal to 0. There's no flux at the outer boundary. Now, you'll find later in the notes I cheat and make this, you can have the ability to find this as something else. The constant pressure outer boundary says that the pressure is fixed at the outer boundary at 0, or the initial pressure, and then the dimensionless pressure is fixed at 0. This is a physically inconsistent situation. The constant pressure boundary, while elegant, is pretty much useless. This is what would happen if we had, there will be a transient flow part of this, but ultimately, what's the behavior for a constant pressure outer boundary? Steady state. Okay. Nobody's asking me why I'm wearing my, 70s evil villain glasses. It's because my super cool purple glasses broke, and I'm really depressed. I've had a bad day, but it's all right. I'll get over it. So the next little bit is talking about the concept. And of course, we have to go back and talk about the radial flow or diffusivity equation again. I know you don't want to do that, but we have to a little bit. Now, I tried to do something here that I apologize for, and that is that I made this completely general. So if you're ever going to work in gas, you can use this development. If you're ever going to work in liquid, you can use this development. But it's a little bit confusing because I defined everything in terms of Y, the letter that comes before Z, so that it would not be P. It can be P, it can be P squared, it can be pseudopressure, it can be whatever you want. And then I also defined it in terms of tau rather than time, so that it could be pseudotime or time. And again, if you don't like that, just say that Y is equal to P and tau is equal to T and work the problems that way. Okay? Again, I was trying to capture every possible scenario. So the inner boundary condition is given by Darcy's law. And again, this silly dy dp, or dy dr and dy dp comes from the fact that we're working in Y and not in pressure. So of course, if you multiply that through, that just becomes pdr. But for the sake of argument, just assume we're working in P. So again, Darcy's law and Darcy's units, and then our gradient term evaluated at the wellbore, and it's equal to a constant. Now, I'm not saying that this is going to happen, but I wouldn't be surprised if later on in this course we didn't talk about the constant pressure case, not the constant rate case. But the constant rate case has some very attractive mathematical aspects, so we're going to work in terms of constant rate. We can then switch to constant pressure or any other scenario using what's called convolution. We'll do that a little later on. Okay. And math ladies, go ahead and correct me here. The magic numbers are 0, 1, and infinity, but the qualification, the asterisk, is that infinity is not a number, but a concept. Is that what we decide? It's a limit. Thank you. Yeah. 26 years of teaching this class, and I just learned infinity is not a number. Thank you for that. Okay, so we'll start by looking at the notes. And again, all of this is old news. We derived all this last week and the week before. None of this should be a surprise. And then I talk about the equivalent liquid case, just so you'll know that we can use pseudopressure, pseudotime. And again, I don't want to, this is like if you're writing a textbook, this is how you would do it. I made it completely general so an idiot could get through it, but then I'm sure it's going to confuse some people. So again, anywhere you see Y, just think P and everything will be fine. So we're going to start on the second page, and we come over to our generalized form of the diffusivity equation. And again, it's del squared Y is equal to phi mu C over K dy d tau. And again, if you don't like Y, put P, and if you don't like tau, put T. Okay. Y can be pressure, it can be pressure squared, it can be pseudopressure, and tau can be time or pseudotime or some other transform time if you want. So we'll just work through it. The form that we're probably going to use the most is form given by 14, which is the radial flow, horizontal radial flow form. There's no tangential flow, there's no vertical flow, and again, this is given from the shell balance concept. If you want me to go back, I can. It's taken from here, so you can use either one of those forms, the expanded form, or this form is the compact form, and this form is the expanded form. We're gonna use the compact form because we need to expand the derivatives. So we'll start with equation 14. The expanded form is the same as we just saw on the previous page, but of course it's in terms of Y and tau. So the first thing we have to do is select our radius. We're going to have a characteristic radius, a characteristic time, and a characteristic pressure drop. The easiest one is the radius. So Alex, RD is defined as R over RW, right? No problem there. Now, the dimensionless pressure must satisfy two conditions. The first condition it must satisfy is that the dimensionless pressure time equals 0 is equal to 0. Duh, that makes sense. How many SPE papers are there written on non-uniform initial pressure? Anybody? I think there's exactly one. Now, if you were going to solve this problem, not analytically but numerically, that wouldn't be a problem. But if you're going to solve this problem analytically, I'd say you're going to be pretty hard pressed not to use a uniform initial condition. Okay? Uniform pressure initial condition. Yes? Yeah, it's a paper by Coble back from the either late 70s or early 80s. C-O-B-L-E, I believe. Okay. And then the second is that the inner boundary condition is the result is this. Okay. And again, this is, I'm being prescriptive because this makes all the other things work out. But we'll get there. There's not going to be any real surprise here. So RD is going to be defined as R over RW. We immediately swap the variables. And so R is equal to RW times RD. Why? Because we're going to substitute that definition of R into equation 14 and just run it through. Okay, I said 14 and this says 15, so my apologies, but whichever one you want, you can substitute it. So you're going to have a partial derivative with respect to RW times RD, and obviously the RW's factor out. So there's an RW, there's an RW, there's an RW, there's an RW, and then of course we don't have anything on this side because there's no geometry term on that side. So you have 1 over RW squared, 1 over RW squared, and then nothing on this side. So what's a logical thing to do, Cam? Multiply through by RW squared. So that cleans up this side, and that was really fast. Okay, that worked out pretty well. Now we need to define our dimensionless pressure function, and that's going to be pretty easy too. It's either Y or P, however you want to define it, but it has to be equal to the initial value of pressure squared to pseudopressure at time equals or less than 0. So that translates into the fact that PD, the dimensionless pressure, has to be equal to 0 for those times. And the only way to do that is to have a dimensionless pressure drop, not a dimensionless pressure, but a dimensionless pressure drop. And unfortunately, we dropped the word drop in the 60s or 70s, but it is pressure drop here. Okay, so first thing we'll do is we'll say the initial pressure minus the current pressure, divide that by the characteristic pressure drop, and what's going to happen is we can rearrange that, and of course when we substitute that into the resultant of equation 18, we have the derivative of a constant, and then the derivative of a constant multiplied by the variable of interest, derivative of a constant, derivative of variable, multiplied by the variable of interest, same thing, same thing. So you end up with all of these terms. Here's the constant, constant, and constant, and then we drop all those because they go away, and then we've got this leftover term here, this leftover term here, and this leftover term here. So we have minus y characteristic, minus y characteristic, minus y characteristic. Cam, I'll give you the glory. What do we do? Just eliminate them. Okay, so now we have d squared pd, drd squared, 1 over rd, dpd rd is equal to this. Okay, we're done, right? It was that fast, except unfortunately we don't know what y characteristic is. So how are we going to figure out what y characteristic is? Well, we're going to use the definition of Darcy's law for y characteristic. Okay, so we come over and we say, okay, Darcy's law, what's your story? It's the velocity is equal to the permeability divided by the viscosity multiplied by the gradient. Going ahead and convert it into y instead of p. Sorry about that. Going ahead and define the velocity is equal to the flow rate divided by the cross-sectional area multiplied by the formation volume factor. No problem there. And now we're starting to get something that looks familiar. We're going ahead and have to add, that the area of the system is 2 pi RH. Okay, this is a cylindrical shell that expands. That's that area term. We've done this before, by the way. So Darcy's law is 2 pi kh over mu b, then this dp dy, and of course if y is equal to p, that goes to 1, and then r dy dr. Okay, again, for the 1,000th time, sorry about the y's, but that's okay. So we set it up as the r dy dr, and we have this term, and of course this is still hanging on, but it'll go away in a minute. And then we evaluate it at rw, and then we're still staring at this saying, well, what the hell difference does that make? So we're going to substitute the definition of RD. We're going to substitute the definition of PD. So the definition of RD is, the definition of R based on RD is RW multiplied by RD. The definition of the dimensionless pressure, substituting the definition for Y is going to be YI minus Y characteristic multiplied by PD. Obviously the constants cancel. There's a constant here, there's a constant here, no problem. This is a constant, so it's going to go away, and we'll be left with that. And of course this is all evaluated at 1. So we're left on the left hand side with all of this, and then we're left on the right hand side with that guy who's new, and then we've left with all this. So what's the logical thing? We want the right hand side to be equal to -1. So I think even, Tom Blasingame, Louisiana Public School Education, I can see that, that's the definition of Y characteristic. I have to make everything go away. Okay? So that's fine. We're done. That's the definition of Y characteristic, and this is our definition of dimensionless pressure for the Darcy unit system. Again, for the 10,000th time, if you don't like Y, substitute P, and everything's the same. So here's all of the possible cases. Here's everything you could do. Sorry about all that. Again, it was just done to make it convenient. So our final form is the same as we saw before, but over here, this is what's left over once we define everything. Now what do? Cam, you want to take a shot, or you want to pass the ball to someone else? Who's your worst enemy in here? Gabe? Gabe, what do we do now? We want to make the coefficient in front of this equal to 1, right? So how do we do that? Well, dimensionless time is equal to time divided by characteristic time, or tau divided by characteristic tau. So we substitute this in, same way we did before, and guess what's going to happen, class? We're going to get all of this stuff, and then we're going to multiply by 1 over time characteristic, and that. So what does time characteristic have to be, Gabe? it has to be this stuff, right? So we're done. So there's equation 44. There's the definition. Well, it's on the next page, but here's the definition of RD. Here's the definition of PD. Here's the definition of TD. So we're completely done, right, class? Okay. Now we have to take the initial condition and turn it into a dimensionless condition. So just by inspection, we can say that if for y, the case of y, r, t less than or equal to 0, it's y sub I. What happens when it's PD, class? It's going to be 0. Okay. Next one, inner boundary condition. We already know that. This is the definition of the inner boundary condition. What is it? We had to use it to get there, so that's, you know, no surprise. We had to use this definition. Next is the infinite acting outer boundary. So the dimensionless pressure as RD approaches infinity for any time or for all time is going to be equal to initial pressure, or what is initial dimensionless pressure? It's 0. So that says that PD for all RD for all TD less than or equal to 0. I did that wrong. Sorry. PD as RD approaches infinity for all TD is going to be 0. Then the gradient term, exactly the same thing as before. We said, okay, we want it to be equal to 0. If that's the case, then we simply go back to the definition that we had before. R dPdR d evaluated at RD is equal to 0. And then last but not least, in the case of constant pressure where it's maintained, the pressure at the outer boundary is equal to PI. Obviously, PD is going to be equal to 0 for all those cases. So there's a very quick, very fast, but very digestible explanation of dimensionless variables. What do we need to do next? What do we need to do next? Mr. Liu? Okay, I agree, but before we do that, let's have a little more pain in our lives. Eric, have you had any pain in your life lately? No? Where's Mr. Desai? He's here tonight, right? Have you had any pain in your life lately? No? Are you happily married? No? Okay, well, I'm just trying to help. Let's see, who hasn't spoken in a while? Ken, you had any pain in your life lately? No? Ricardo? No, nothing. Miss Jen, no? Okay, nobody's going to say. Oh, you had some pain, but you don't want to talk about it. Okay. What are we going to do for pain? We're going to do this one time and one time only. We're going to derive the definitions of the dimensionless variables in field units. Now you can do metric units if you want. It's on the other page, but we're really only interested in field units. Cam, did you have to do this at Penn State?
I think at some point.
Okay. Gabe? You never did because nobody makes you do this in undergrad, do they? Okay. Eric? You've blanked it all out. You don't think Dr. Ozcan did this to you? Okay. So everybody always hated this in undergraduate, but you do it once, you do it right, you never forget it. So what are we going to do? We're going to take the definition of a Darcy, which is Darcy units, because we work in Darcy units. We're going to convert our problem into Darcy units. Is that right? Well, it's not really how the words go together, but that's actually what we're going to do. We're going to start with what we want and work our way back to Darcy units, which gives us what? The coefficient of what it takes to go backwards and forwards. So very quickly, what are our units for Darcy and flow? cc's per second, right? Atmospheres, centimeters. What was the unit for viscosity? It was centipoise, so we got lucky there. What's the units of viscosity for the metric system? What is it, Mr. Sarkar? Pascal seconds, correct. Yeah. I mean, there's different metric systems, but the field units version of the SI for petroleum engineering is Pascal seconds, for whatever anybody cares about that. All right, so now we start with, again, the definition of a Darcy, and we come over here. How many of you know these by heart? How many of you have these memorized? How many of you never want to memorize these? How many of you want to work in the metric system? Joker. Do they work in the metric system in India? In tons? Yeah, just like in China and in Russia, right? Okay. But I'm sure they buy it by the barrel. No offense. Okay, so we'll start over here. Here's the definition of dimensionless pressure. Here's the definition of dimensionless time in Darcy units. So that corresponds to this system of units. So how do we work this? Well, we want to work in millidarcies because that's what field units are in. How many Darcys are there in a millidarcy? Well, there's 1,000 millidarcies in a Darcy. We work in feet. I know one of those. You're right. I'd like to know whose foot was a foot, but and then they're 30.48 centimeters per foot. That's exact. And then that's fine. That canceled. Then we work in this thing called PSIA. And 1 atmosphere is 14.696 PSIA as a conversion. We work in cc's per second over here. What do we work in the petroleum industry? Stock tank barrels per day. So we're going to have 5.615 cubic feet per barrel, 30.48 centimeters per foot. That's going to end up getting cubed. 1 day is 24 hours. 1 hour is 3,600 seconds. Okay, you guys got a feel for this? How many seconds are there in a day? Where'd you memorize that from? Really? I'm impressed. Is that like some, you know, I miss you 86,400 times a day? Yeah. Very good. Why do you need to memorize that number, class? When you're using a memory pressure gauge, how many points can you store? Sorry? They come in increments of 1,000,000. So if you're going to measure pressure every second, you've got about, 10 days? You want to give yourself some slack. So, just be careful. I've seen people sample every second and then wonder why they ran out of memory on their memory gauge. Of course, the best thing to do is get a surface readout gauge, and then you can store everything, but that's okay. Very good, Gabe. You get a hug. And now we have reservoir barrels per stock tank barrel, which doesn't really matter because that's dimensionless. Viscosities and centipoise, and then this silly thing, which doesn't matter anyway. So we multiply all of these numbers out, and we have 2 pi multiplied by 1.127 times 10 to the minus 3. What is 2 pi multiplied by that, class? It's 7.081 times 10 to the minus 3. What is 7.081 times 10 to the minus 3? It's 1 over 141.2. Now do you recognize this, Cam? Now do you recognize this, Eric? Now do you recognize other petties, can, etc.? Okay. And then for TD, we have millidarcies to darcies, no problem. We have seconds to hours. Remember that we work in hours in well testing and in days and for production, which is kind of frustrating. Porosity is a fraction, viscosity is in centipoise, total compressibility is in PSIA, and then we have 14.696 PSIA. And of course we have the RW squared, which is in feet, so 30.48 centimeters squared. Work all that out. It is 2.637 times 10 to the minus 4th, or in terms of days, it's 0.0633. Okay, so there, we finished, and you guys can do the other ones on your own. We'll take a one.